finishing up in these ideas of Chapter 7 and focusing more in on this electron dot structure idea. In the previous previous video, we talked about these steps for drawing these molecules, and there's some examples of these in the book, and I'd encourage you to take a look at those. And we're going to work some of these out on the board next time we meet. And one of the ideas I do want to get across here is that sometimes the octet rule is not explicitly followed. When it's not, one of those cases obviously is hydrogen. Hydrogen only needs 2 electrons rather than 8 to fulfill its octet, so it just makes a single bond with no lone pairs. But there are other cases that we find exceptions to the octet rule on the central atom. For example, boron is very, very small, so it can make a compound where it has 6 valence electrons instead of 8 and is still fairly stable. And so we'll look at an example of that in class. But the other one, and the more common exception, is notice back on step 3, I said add lone pairs so that each peripheral atom except for hydrogen gets its octet, and then place all remaining electrons in lone pairs on the central atom. Well, that could cause you in some cases to put more than 8 valence electrons around the central atom. Additionally, some atoms have more than 4, maybe 5 or 6 bonds, and therefore have more than the octet around them. This will only happen with elements in the 3rd row of the periodic table or lower, so sulfur, phosphorus, xenon, iodine, chlorine, so on. It will not happen with 1st or 2nd row elements. And we'll work some examples of that in class as well. Once in a while, and we'll work some examples on this, ozone is a perfect example of this. Once in a while we'll find examples of compounds where it's possible to draw 2 different valence structures for the same molecule, moving only electrons to different positions and not moving the atoms. And like I said, you can look at this in your book or online. Ozone and benzene are the 2 classic examples, and we'll work these out in class as well. But the interesting thing about these kinds of compounds is most of the time what exists is not either of your drawings, but an average between the 2. So for benzene, where we have alternating double bonds, we have a ring of 6 carbons with alternating double and single bonds between them. And we can always move the double bonds to different spots and still have a valid structure. But what exists is average a bond and a half between each carbon. Now we call that a resonance hybrid. It's very difficult to draw the molecule as it actually exists, but we can draw the 2 separate structures and say what exists is a resonance hybrid of those 2 structures. Once in a while we'll find 2 or more non-equivalent ways to draw a particular molecule, one of which is more valid than the other. And the way that we'll determine which is the more valid of the 2 or more drawings is by counting up the formal charge. It's a measure of this is a little bit different than charge, and it's different from oxidation number. What we're measuring is the number of valence electrons the atom has. So we look at the periodic table. Sulfur has 6 valence electrons, for example. Oxygen has 6. Fluorine has 7. We take that number for a particular atom and subtract the number of valence electrons assigned to the bonded atom, and that's a very key word. We have to define what we mean by assigned. An electron is assigned to the atom if it's one of the bonding electrons, and here's the definition. In a bond, as far as formal charge calculations are concerned, half of the electrons in each bond are assigned to a particular atom. So if an atom has 4 bonds, then we would put 4 here. Half times 8, because there's 2 electrons in each bond, would give you 4. But any lone pairs that are on that atom belong only to that atom. So the number of Non-bonding electrons are 2 times the number of lone pairs. It gets written here, and we're going to work a few examples. Sulfate ion is a very interesting example of this, because it's easy to draw sulfate ion with all single bonds, and octet rule is satisfied. But what satisfies the formal charge rule is a drawing where 2 of the oxygens on sulfate are double bonded and 2 are single bonded, and therefore the sulfur is violating or acting as an exception to the octet rule, and that is the best drawing for sulfate ion. So what we're going to find is that more often than not, the drawing that is the best drawing is going to be the one that has most atoms at 0 formal charge, or at least as close as possible to 0 formal charge. And when all of the atoms cannot be 0, then only the most electronegative atoms on the molecule should have a negative charge, or if something has to have a positive charge, only the least electronegative atoms on the molecule should have that charge. And like I said, some of these topics that we've covered in this chapter are much more easy to demonstrate or easy to teach in class with a whiteboard working out problems. So that's what we're going to be spending most of our next class or 2 doing. In the meantime, here is a set of problems you guys can be working on your own, and using the textbook to try to help you work out. And when you run into, or if you run into trouble with any of these, those will be some of the ones that we'll work the most diligently on in class.